Dear students, this week we will discuss the pathophysiology of electrolyte disorders. As an introduction, I would like to present that the composition of our body, as you know, is made up by primarily only few chemical elements, carbon, hydrogen, nitrogen, and oxygen, and in sharp contrast with plants, in animals the main component in our body is sodium, while in plants the main cation, even extracellularly, is potassium, and while in mammals and human beings the most important serum anion is chlorine. In plants it is phosphorus. You can see that zillions of trace minerals play an important role in human metabolism, mainly as catalysts or other activators of enzyme systems. Regarding gender and age, the composition of our body changes and different. For instance, in man, the ratio of water and fat is and protein is different from women, because in women the proportion of fat which plays a role in supportive and endocrine organ is more important than in men. In the embryo, water content is extremely high, but in older adults, as you can see, it is just half of the embryo and the fetus. As you know very well from physiology and from your high school studies, the majority of body fluids can be found intracellularly, and extracellularly the majority is interstitial, and only 5% of the total volume, 60%, is intravascular. In this slide, I would like to summarize water and salt handling in the kidney with the mechanism of countercurrent multiplier. In parallel with the countercurrent multiplier of the perfusion of the extremities. Countercurrent multipliers serve only a single purpose. Their role is to separate facultative and obligatory transports, while in one limb without countercurrent it would be necessary to transport at the same time in a connected manner the waste products and water and electrolytes in countercurrent multipliers, you can separate them. Quite interestingly, using 3 limbs of the countercurrent and 2 countercurrents, I mean the vasa recta and the tubuli, you can set up a system in the kidney with which you can completely separate water and electrolyte transport and waste product transport. It's pretty similar to the transport in the extremities, but while in the extremities, the facultative transport means heat dissipation or heat conservation, the obligatory transport consists of the transport of nutrients, oxygen, and carbon dioxide. When you want or your body requires to transport them separately, so it is needed to, or obviously it is important to maintain the transport of nutrients and oxygen. For instance, in a cold ambient temperature, but at the same time, you want to reserve, you want to keep as much heat as possible in your body. You will set up shortcuts between the arteries and the surrounding 2 veins. They run in a common sheet which contains smooth muscle fibers. Obviously, when this common sheet is constricted, then the shortcuts are established and heat will be dissipated into the veins, and less heat, actually brown movements and photons, are available for heat dissipation. These shortcuts are essential because with that shortcuts you can retain heat. At the same time, you can maintain the necessary food and nutrient transport. However, in warm conditions, when you want to dissipate more heat, you will completely separate the flow between the arteries and the veins, and therefore the obligatory and facultative transport are linked and are not separated from each other with shortcuts. And that's way heat and nutrients will be transported to the periphery and heat will be dissipated in the same manner. The most important aspect in your body to establish shortcuts with the help of ADH and aldosterone-mediated transporters and natriuretic peptides regulated transporters between the limbs. With that, you can retain fluids if your fluid or sodium supply is restricted, while in the case of fluid overload and sodium overload, you can close these shortcuts with the elimination of hormone secretion, and parallel with rest nitrogen and other rest substance transport, you will lose sodium and fluid. For instance, in the most important rest materials, rest compounds are rest nitrogen compounds, urea, creatinine, uric acid, but also you are supposed to waste rest materials, waste materials even from plant origin, like potassium and phosphate. In this slide, I will summarize the main physiologic and pathophysiologic regulators of water and salt balance. You are supposed to clearly understand that the primary regulators are ADH, aldosterone, and natriuretic peptides, which are stimulated by osmoreceptors and baroreceptors. Baroreceptors play a critical role in the whole process because they both are able to modulate the vasopressin secretion, and also they are important in a natriuretic peptide secretion. Also, it's important to emphasize that changes in these regulators, in hormones, or overload either by water and fluids can lead to different alterations of volume and sodium concentration. Here you can see in gray boxes those issues which are related to hypernatremia, while those dotted ones which are related to hyponatremia. In general, we classify sodium and water homeostatic abnormalities as commensurate changes or disproportionate changes. So when you have a proportionate change in sodium and water, then it means that isotonic fluid is taken up in excessive amount or lost in excessive amount. The other mechanism, the opposite block, involves those mechanisms when you will lose disproportionately sodium or water. Obviously, when you lose water, predominantly hypernatremia will develop, while when you lose sodium, disproportionately hyponatremia will develop. Actually, isotonic fluid intake and deficit are much more complex situations and more difficult to handle, especially those instances when you have isotonic fluid excess. Isotonic fluid deficit and hyponatremia and hypernatremia can be handled in a relatively easy manner, because increase in aldosterone or decrease in aldosterone parallel with decrease in ADH or increase in ADH can help in the manipulation of either hypo or hypernatremia. It goes for isotonic fluid deficit as well, when parallel increase in aldosterone and ADH concentration will manage the situation. However, it is not the case in isotonic fluid excess. In isotonic fluid excess, the regulation of both previously mentioned hormones is accompanied by a single factor of natriuretic peptide release. They play a very important role, AMP and BMP release, in the management of such situations. As you know very well, sodium concentration is the reference range is between 145 and 135 millimole per liter, and the hyponatremia obviously consists of situations when the sodium concentration is less than 135. Actually, the classification of hypo and hypernatremias are really complicated, but since these conditions are extremely common and you can encounter zillions of situations which are, as I mentioned, can reflect bewilderingly complex background. So demonstration and detection of hyponatremia or hypernatremia is a very important clue in your diagnosis. And the following algorithms will help you to establish the cause of this ominous sign. And that's why it is so important. You can use these slides and this lecture as a reference for your later studies as an algorithm, because, as I said, it is a very common thing and very difficult to tell what is the nature of the process which can be found in the background. So hyponatremia can be either hyperosmotic, isosmotic, or hypoosmotic. So when you realize hyponatremia, the first thing you are supposed to do is detection of osmotic activity of the plasma, and from then onwards you can get further. In hyposmotic hyponatremia, there are three further categories. One group is hypovolemic, isovolemic, and hypervolemic hyponatremia. Here you can see a short summary of hyponatremias, which can be further classified into isotonic, hypotonic, and hypertonic ones. The biggest group is obviously hypotonic hyponatremia. Rarer conditions are isotonic and hypertonic ones. In the least common one, which is isotonic hyponatremia, actually you can see a pseudo hyponatremia. We will discuss later. In this condition, you can see accumulation, chronic accumulation, usually chronic accumulation of osmotically active substances in a compartment which otherwise doesn't contain commensurate amount of sodium. In hypertonic hyponatremia, tonicity is higher than in normal circumstances, and it is related to either hyperglycemia, so endogenous sources can be one factor, or also osmotically, due to osmotically active substances which will get into the circulation due to therapeutic purposes, like mannitol sorbitol, which is used for decreasing the brain volume in conditions when brain edema is a threatening complication. So imminent cases you will administer it, but overdose can lead to hypertonic hyponatremia. Also radio contrast agents can elicit a similar condition. In hypotonic hyponatremia, you can differentiate between the groups among different groups according to the total body volume. In hypovolemic one, you can lose fluid either through the gastrointestinal tract or through your skin, all in all extrarenally or renally. Nevertheless, these sort of losses are accompanied by some sort of compensation in the form of free water, and this free water uptake will lead to hyponatremia. In euvolemic form, the main issue is usually free water clearance or free water management, either increased uptake of free water or typically in biopotomania or tea toast diet, or decreased free water clearance in syndrome of inappropriate antidiuresis, or other sources of ADH, for instance, in the case of activation of the hypothalamic pituitary adrenal system, and in that instance, not the posterior lobe of the pituitary, but the hypothalamic nuclei are the source of vasopressin, which plays in that instance a role in the activation of the stress axis, but as a side effect it will upregulate free water retention. In hypervolemic one, you can summarize this condition as the edema state, which can be related to either increased hydrostatic pressure, decreased oncotic pressure, or increased membrane permeability. A short summary of the two smaller groups. In hyperosmotic hyponatremia, which is a pretty common disorder, specifically when it is an endogenous, when the osmotically reactive substance is of endogenous source, you can see accumulation of glucose in the extracellular compartment, typically in hyperosmotic crises in type 2 diabetes, and this sort of accumulation actually decreased ingress of glucose by insulin deficiency. Relative insulin deficiency to the intracellular compartment will elicit shift of water from the intracellular compartment, and definitely and inevitably it will lead to dilution of sodium in the extracellular compartment. Obviously, in that instance, the treatment is rehydration and insulin administration. In isosmotic hyponatremia, there is a group which is true isosmotic hyponatremia, when isosmotic fluid will get into the circulation, usually due to surgical interventions, typically in transurethral prostate gland resection. But the majority of the cases are the pseudohyponatremias. Pseudohyponatremia is another group of the isotonic conditions. Actually, they represent a chronic condition and at the same time a laboratory artifact, measurement issue. In those instances, a relatively high volume of proteins and lipids will accumulate in the plasma, and this compartment doesn't contain proportionally high sodium ions, and therefore when you measure only in plasma water, you will get correct measurement values, but when you use a different measurement method like flame photometry, when you separately measure the ion content and the volume of the sample, you inevitably end up with false measurement values. Why? there are two types of measurement methods at your disposal, one expensive and one cheap, and another one which is cheap. The expensive one will directly measure the ionic activity through the measuring electrode membrane. They are the so-called ion selective electrodes, which work like pH meters, and they will measure the direct flux transport of a given ion with the measurement of impedance and conductance of the ion through the membrane. Unfortunately, these electrodes must be regenerated regularly, and that's why this process is expensive. Flame photometry uses a completely different approach, not direct measurement, and it will measure separately the ion content and the volume. Volume measurement. After volume measurement, you will actually heat and burn the sample, and it will lead to activation of metallic ions in the sample. Electrons from the inner pathways will go to outer pathways, and this sort of activation, excitation, over time will lead to return of the electrons into the inner pathways, and parallel with that you can see the emission of photons of absolutely specific wavelength, and these photons as fingerprints will show the presence and parallel with it proportionally the amount of ions in the sample. So you can measure actually the direct content of a given ion in the sample, and previously you measured the volume. When you compare them and you divide them, you'll get the concentration. But unfortunately, when you burn the sample, you measure also the ion content in the protein and lipid compartment, which actually contain very small amount of sodium and other ions. Hypoosmotic hyponatremia is the third group of hyponatremic conditions. In that disorder, hypotonicity is the most important characteristic feature which accompanies hyponatremia, and they can be grouped into three group, as I mentioned previously. The biggest one is the hypervolemic one, which can be summarized as edema states, edemic conditions. Hypovolemic hyponatremias are the conditions when you lose either hyperosmotic hypernatremic fluids, or you will lose isonatremic or even hyponatremic volumes, but this sort of depletion is somewhat compensated by exclusive uptake of free water. In isovolemic or euvolemic hyponatremia, the initial and the main problem is free water clearance abnormality, which can develop due to either increased free water uptake, like beer potomania, tea toast diet, psychogenic polydipsia, stress-induced uptake because the patient osmotic threshold changes, or due to abnormality of thirst sensation, or the other option is when you will secrete high concentration of ADH, and ADH will lead to excessive free water reabsorption, and free water reabsorption will be compensated by decreased aldosterone secretion and increased secretion of natriuretic peptides, and this sort of compensation will lead to iso or euvolemia at the expense of hyponatremia. So, in hypovolemic hyponatremia, total body sodium will decrease, and proportionately is much bigger than total body water loss. For instance, as I mentioned, gastrointestinal losses in third space or complete losses into the third space, burns, pancreatitis, traumas. While renal losses, specific diuretics which interfere with sodium transport, like thiazide diuretics, which interfere with sodium chloride transport in the thick ascending loop of Henle, or aldosterone antagonists. Some forms of salt losing nephropathy, when the kidneys sodium retention is inhibited by ions in the ultrafiltrate. For instance, bicarbonate can obligate such processes, or typically in conditions when the patient loses ions due to chronic tubular reabsorptive disorders. Primary adrenal cortex cortical insufficiency in Addison's disease, loss of sodium, specific loss of sodium, is related to decreased sodium reabsorption, as decreased sodium reabsorption will lead to compensatory ADH release, and ultimately it will lead to dilution. Actually, the volume will be still less than in normal circumstances. In iso or euvolemic hyponatremia, you can see, as I said, increased relatively higher sodium activity and less glucocorticoid activity. So activation of the ADH secretion, or due to decreased glucocorticoid secretion, compensatory overactivation of the CRF ACTH axis, and parallel with CRF, you can see the activation of ADH secretion, which will lead to volume retention. Syndrome of inappropriate and diuresis, or SIAD, was mentioned previously in the previous semester. It is just a short recapitulation. It can be related to malignancies and activation of the enterochromaffin cells in the pulmonary system, in the CNS, and it is usually characterized by increased water reabsorption, actually decreased free water excretion, which will be compensated by increased secretion of natriuretic peptides, AMP and BMP, and decreased aldosterone secretion. So the compensatory reactions will be sufficient to balance the volume retention, but it happens at the expense of sodium concentration. That's why it is important to emphasize that volume regulation is more important. It prevails over sodium regulation. So it is a sort of maladaptation. In some instances, not the abnormality of vasopressin release or overactivation of the stress axis can be found in the patient, but you can detect that the patient consumes less osmotic substances than in normal circumstances. Since the kidney has a given maximal dilution and the concentration capacity, when you overload the patient with volume without proper addition of osmotically active substances, you can easily reach the limit of free water clearance. At that level, the kidney cannot dilute more the urine, and fluid, free water, will accumulate in the patient. If you don't consume at all osmotically active substances, even 4 liters of water can elicit such a hyponatremia, which can be dangerous. But with proper consumption of osmotically active substances, the limit is much higher. It is 20 liters of urine. So you are supposed to know that this critical 4 liters can be counterbalanced with proper consumption of osmotically active substances, which is obviously can be difficult in the case of malnutrition or in the poor. Here you can see summarization of syndrome of inappropriate antidiuresis, the causes: malignant diseases, pulmonary disorders, central nervous system disorders, drugs and other causes, genetic reasons, for instance, gain of function mutation of the vasopressin receptor, and all of them can be fitted into the previously mentioned categories. Hypervolemic hyponatremia. As I said, these conditions can be summarized shortly as the edema states. They can go with either underfilling or overfilling. Typical underfilling situations are congestive heart failure. In that case, hypoxia elicited increased membrane permeability in the capillaries, liver congestion elicited hypoonchia, and back foot failure elicited increased hydrostatic pressure will lead to underfilling. In hepatic insufficiency and cirrhosis, accumulation of edema fluid will appear in the peritoneal cavity as an ascites, and it is related to liver failure and hypoonchia, liver inflammation and inflammatory mediators evoked increased peritoneal membrane permeability and vasodilation, and ultimately decreased production of proteins and hypoonchia in cirrhosis. In nephrotic syndrome, the most important reason is pure hypoonchia related to massive and selective proteinuria. In advanced chronic renal insufficiency, the most important reason is overfilling due to fluid retention and increased hydrostatic pressure, which will lead to secondary fluid loss due to mainly increased membrane permeability evoked by the inflammation in the kidney and the cytokines secreted by the inflammatory cell. Here you can see the distribution of edema fluid in a normal subject, and you are supposed to understand clearly that in an edematic subject the plasma volume is the same, and that's why it's very important to detect the the accumulation of fluid in the interstitial compartment, because it is the place where edema fluid actually will accumulate. Another important aspect, that in some instances the plasma volume is just or even hardly reaches the normal volume, and that's the initiation which will cause edema accumulation. It is the so-called underfilling process. What does it mean? In underfilling, the primary initiating event is fluid loss. Fluid loss due to either increased venous pressure or, for instance, due to decreased oncotic pressure. Due to decreased oncotic pressure, typically in nephrotic syndrome or ascites, or in decompensation of the heart due to increased hydrostatic pressure, backfed failure of the heart, excessive amount of fluid will be accumulated in the interstitium, and that sort of shortening in the intravascular compartment will evoke secondary changes which try to re-establish and normalize the plasma volume. These sort of compensatory mechanisms involve ADH, aldosterone hypersecretion, so a secondary hyperaldosteronism, and inappropriate ADH response, plus downregulation of natriuretic peptide secretion. The other option for edema formation is the overfilling. In the overfilling process, the primary event is fluid retention. Such happens in nephritis syndrome. In nephritis syndrome, the primary event is oliguria, anuria, and these retained fluid will elicit increased hydrostatic pressure, and this sort of increased hydrostatic pressure accompanied by increased membrane permeability elicited by cytokines due to the heavy inflammatory process in the kidney will elicit edema formation, but this sort of edema formation is secondary. The next chapter is hypernatremia. Hypernatremia states in a similar manner to hyponatremia can be further subclassified. In all of them, you can see that edema cannot be detected, and their volume, the volume state, can be also hypovolemic, euvolemic, or hypervolemic. In hypovolemic states, you can find the same thing: extrarenal loss, renal loss, in the same manner, but in those instances, in sharp contrast with the hyponatremia states, you cannot detect at all water replenishment and water intake, no compensation, and therefore hypovolemia will strictly go with hypernatremia, because in that cases you will lose predominantly hypotonic, hyponatremic solutions. In euvolemic states, euvolemic hyponatremia, you will see just the opposite of the euvolemic hyponatremia. While in euvolemic hyponatremia, the overactivation of vasopressin secretion was the primary problem. In here, insipid diabetes, diabetes insipidus, is the most important reason, or in some instances hypodipsia. Rarely, extrarenal losses can cause a similar situation, but in those instances you will lose pure water, typically due to perspiration or due to respiration. In hypervolemic hypernatremia, you can see specific conditions of high of sodium gain, in which selectively you can intake or you reabsorb fluids of high sodium concentration. They are relatively rare conditions. So in hypernatremia, you can see that the sodium concentration is bigger than 145 millimole per liter, and in the hypovolemic hypernatremia, the predominant feature is free water loss, or you can see a combination of sodium and free water loss, but relatively free water loss is bigger and never properly, never compensated. Extrarenal or renal loss accompanied by hypodipsia. When you lose fluids extrarenally, typical examples are diarrhea, vomiting, or third space losses. Renal losses are usually related to massive loss of ions which are able to drag sodium ion. For instance, in diabetes, when ketone bodies will bind sodium ion and they will be lost in excessive concentration. Isoeuvolemic hypernatremia, as I said, predominantly these are the diabetes insipidus conditions, which can be either, as we discussed in endocrinology, central diabetes insipidus, when the secretion of vasopressin is afflicted, typically pituitary stalk injury, or it can be a nephrogenic diabetes insipidus, or in some rare instances it can be a gestational diabetes insipidus. In gestational diabetes insipidus, the main problem that in some forms of complicated pregnancies, like in twins, in the case of twin pregnancies, you can detect excessive activity of the placenta to decrease the concentration of vasoconstrictor substances. And the most effective metabolic pathway to elicit this is the secretion of vasopressinase. And vasopressinase will decrease the vasoconstrictor tone upon the placental blood vessels, but at the same time, unfortunately, will decrease vasopressin concentration in the total body circulation. And the last one is, as I said, the nephrogenic form, when you have a mutation or a acquired form of kidney disorders, when the kidney either congenitally or in acquired form cannot respond to vasopressin. Pathologic reasons can be, secondary reasons can be some drugs, infections, while the congenital forms of receptor mutation or equiporin channel mutations. So in diabetes insipidus, the most important process is primary fluid loss due to increased free water clearance, and it will lead to increased fluid intake, and parallel with that, aldosterone secretion will increase, and the AMP and the BMP secretion will drop. So altogether, relative salt retention can be detected, and that's why hypernatremia will develop in the patient. Hypervolemic hypernatremia is a rarer group of hypernatremic conditions, but consists of two completely separate groups. The first group is related to primary sodium retention, which can be caused by primary aldosteronism, like Conn syndrome, or pseudo hyperaldosteronism, when actually aldosterone level is normal, but either the activity, the action of aldosterone is aggravated, or some other substances will mimic the action of aldosterone. For instance, glucocorticoids, when they saturate 11-beta hydroxysteroid dehydrogenase, like in Cushing's syndrome or Cushing's disease, will elicit mineralocorticoid effects, or the congenital form when the enzyme itself is missing. In some instances, mineralocorticoids like substances or substances of mineralocorticoid activity, like DOC, will accumulate in the plasma, or gain of function mutation of the mineralocorticoid receptor will elicit the same clinical picture. And the last one, when the primary problem is related to the kidney itself, and due to tubulopathy, you can see increased avidity for sodium, and the aldosterone level is actually lower than normal circumstances. The other group of hypervolemic hypernatremias are actually overfillings, or primary sodium gain disorders, in which usually due to clinical issues, due to malpractice, the patient is overloaded by solutions of high sodium content. For instance, in metabolic acidosis, treatment with sodium bicarbonate. Chloride is the most important anion of the extracellular compartment, and it plays an important role in gastric juice formation, chloride bicarbonate shift, pH regulation, and in general, it follows sodium balance, but as you know, in some instances, it can be a separate abnormality. For instance, secretory diarrheas evoked by either enterotoxinogenic E. coli or Vibrio cholerae strains, or a very common congenital disorder, cystic fibrosis. You can find selective loss of chloride and only a secondary loss of sodium. Much rarer channelopathies can be responsible for loss of chloride in the colon or in the kidney. In all these conditions, as I mentioned, not sodium is the primary problem. Sodium loss is the primary problem, but chloride loss. And in these instances, sodium will just accompany the condition. Taking your knowledge into consideration in acid-base balance, you should remember that chloride is a very important index of acid-base balance changes, because in a normal chloremic metabolic acidosis, you can see an increased anion gap, while in hyperchloremic metabolic acidosis, the initial problem is bicarbonate loss, and due to shrinkage of bicarbonate volume and loss of bicarbonate, sodium can be reabsorbed only with the together with chloride, and that's why it will lead to accumulation of chloride in body fluids. While metabolic alkalosis can be again further classified into chloride responsive and unresponsive forms. In chloride responsive form, the initial problem is loss of chlorides and volume, and while in unresponsive forms, the main issue is gain of volume and gain of bicarbonate, and in those instances you cannot see changes in chloride concentration. Here you can see the structure of CFTR protein, which is an important regulatory factor of chloride permeability. There are at least 12 or 1500 mutations which will influence the structure, post-translational modification, function, and lifespan of the protein. Some of them which will lead to a knockout mutation are ultimately dismal prognosis and lethal disorders. ATP binding and mobilization happens through these domains. These are the regulatory domains which are targeted by protein kinases, and here you can see the pore of the protein. Chloride transport and loss of chloride can be elicited by the influence of cholerotoxin directly upon CFTR, or can be influenced by enterotoxigenic E. coli, which will influence the cyclic GMP level of produced by guanyl cyclase, and these cyclic GMP increase in cyclic GMP will lead to increased chloride flux and decreased hydrogen decreased sodium reabsorption, which will altogether lead to diarrhea. It's very important to emphasize that it altogether, as you can see, such toxins like cholera toxin and enterotoxigenic E. coli toxin are effective modificators of such CFTR molecules, which are not completely missing, but somewhat sluggish in activity. Therefore, it's a viable option to modify their function with these toxins and to activate them or to facilitate their function in and therefore at least some in some organs, the compensation of the dysfunction is an achievable goal. As you can see, in the gastrointestinal tract, the main role of CFTR is a service of bicarbonate transport, and chloride channel is interlinked with bicarbonate secretion. In the sweat duct, CFTR is responsible for chloride reabsorption in parallel with sodium reabsorption. So when it doesn't function, the outcome will be chloride and sodium loss. While in the mucous membrane, the orientation is just the opposite. It is responsible for primary chloride secretion, and parallel with that, decrease in sodium reabsorption by the epithelial sodium channel. If CFTR cannot function properly, chloride cannot be excreted, and sodium reabsorption will be excessive, and it will be accompanied by excessive amount of water reabsorption and mucus dehydration, and this sort of thick mucus will completely inhibit the normal mucociliary clearance process, and it will lead to congestion of the mucus and therefore proliferation of bacteria in the respiratory system, which will make you prone to develop chronic respiratory infections, usually by opportunistic microorganisms like Klebsiella, Pseudomonas, and Proteus. Potassium balance. Potassium is the most important intracellular cation, and it takes part in metabolism. It is an important regulator of the component of the transmembrane Donan potential. In general, you can say that in hypokalemia, the membrane is obviously hyperpolarized, because the extracellular concentration is even less than normal circumstances. When in hyperkalemia, you can see that the membrane is more excitable because it is depolarized. Potassium balance is regulated not only by the uptake, that's why it's important to emphasize due to the difference in the concentration in the extra and intracellular compartment, but very importantly, you should emphasize that the transmembrane transport is at least as important. They can be either active or passive transport processes. The transcellular distribution and transport is influenced by catecholamines and insulin, aldosterone. All of them act on the sodium-potassium ATPase, either directly or due to the ATP supply. Also important factor in the transmembrane shift, the hydrogen ion potassium ion flux or exchange process. That's why in acidosis hydrogen ion will enter the cell, and as a buffering activity, potassium will leave the cell, and during alkalosis just the opposite will happen. Here you can see a nice summary of deranged potassium metabolism. First, hyperkalemia and the related disorders. As you can see, transmembrane transcellular shift is one reason for hyperkalemia. For instance, due to ATP deficiency, abnormality of the sodium-potassium pump will lead to leakage of potassium and hyperkalemia. Also, insulin deficiency will elicit the same process, and abnormality of hydrogen ion potassium transport in the transmembrane passive transport will elicit outflow of potassium from the membrane. Also important that cell death will lead to release of potassium, and you know that the intracellular concentration of potassium is around 100 millimole per liter, so even minor disruption and dysfunction of the cells will lead a huge amount of potassium release. Increased potassium retention can be found in conditions which can be summarized as or can be characterized by decreased GFR or inefficiency of aldosterone, because aldosterone is responsible for not only sodium retention but also potassium waste excretion, which comes from plants. In general, hyperkalemia will lead to depolarization, and this sort of depolarization for a while will lead to increased potassium conductance, and due to this process, also you can see a much faster repolarization phase in the action potential, and that's why you can see bigger and bigger T waves on the ECG. Hypokalemia is related to just the opposite situation. So uptake of potassium into the cells, for instance, due to alkalosis, insulin, or due to diuretics, hyperaldosteronism, decreased uptake, and in general it will lead to hyperpolarization, decreased neuromuscular excitability, and repolarization will be delayed, which will appear as a profound and conspicuous U wave on the ECG. So, alterations of potassium homeostasis, as I said, can be described, grouped into different forms. The first one, when the reason is just transcellular distribution problem. In the second one, you can see indeed depletion of potassium, and it is accompanied by a commensurate decrease in serum potassium level. And the third one, in which there is a massive potassium depletion, but it is masked by transcellular shift, and it cannot be detected in the form of hypokalemia. For instance, in severe renal failure, despite depleted potassium stores, you can see hyperkalemia, which is elicited by acidosis, or diabetic ketoacidosis. Massive loss of potassium can be found. This massive loss of potassium is evoked by ketonuria, and ketone bodies will grab not only sodium but also potassium. So in general, you will lose huge amount of potassium, but massive acidosis will elicit shift of potassium from the intracellular compartment to the extracellular, and it will completely camouflage total body potassium loss, and it is very, very difficult to diagnose and misleading condition. And when you try to treat, first you want to try to treat acidosis of the patient can die, because rapid and inadvertent treatment of acidosis will lead to immediate shift of potassium into the intracellular compartment, hypokalemia, and fibrillation will develop. So in the case of such situation, the first thing is insulin plus glucose, and parallel with that, or later and rehydration and volume supply, and the last thing you should try is the treatment of acidosis. Also, it's important congestive heart failure, when you have a massive systemic depletion of potassium due to compensatory hyperaldosteronism and due to a very frequent treatment with diuretics. So hyperaldosteronism and potassium wasting diuretics will elicit massive total body potassium loss, but due to acidosis you cannot detect these hypokalemia. Going back to the extra intracellular shift cases, so as I said, hypokalemia can be elicited by insulin administration, catecholamine release or therapy, redistribution in alkalosis. Treatment of pernicious anemia is a very important, and practically every form of rapid cellular proliferation processes can lead to insidious development of hypokalemia due to lots of intracellular compartment is produced, and intracellular compartments are produced, and they will take a huge amount of potassium. So potassium supply is very essential in those cases. Selective accumulation of potassium in the cells can be found in all those cases when drugs will inhibit the exit of potassium from the cells. Hypokalemia, together with depleted body potassium stores, can be found in malnutrition, alcoholism, and extra renal and renal losses. Typically, renal losses are related to diuretics or kidney conditions when the tubuli cannot cannot respond to regulators, or they compensate for decreased GFR. Gastrointestinal loss is usually related to vomiting or diarrhea. Some hypokalemic conditions are accompanied by hypertension, and all of them are related to overactivation of steroid hormones, either direct mineralocorticoid activity, for instance in hyperaldosteronism, so in Conn syndrome, or as a side effect of other hormones which have some sort of mineralocorticoid activity. For instance, Cushing's syndrome is such a condition. There are kidney conditions which go with decreased or normal blood pressure. They go together with primary potassium loss. In those conditions, potassium cannot be reabsorbed either by a congenital disorder, for instance, congenital tubulopathies, or renal tubular acidosis, or Bartter syndrome, or diuretics, or osmotic diuretics will drag sodium. It is the so-called dragging mechanism. Hyperkalemia is a condition when potassium level is higher than 5 millimole per liter, and the first situation, which is very frequent in clinical settings, is pseudohyperkalemia. In those cases, you can detect increase, laboratory increase in potassium level, but it is due to usually an artifact because of the storage of blood samples, and from the cells which contain huge amount of potassium due to decreased ATP supply and developing acidosis. The potassium will leak out, and that will modify the actual potassium concentration. So it's related to usually long storage. Let's see, the samples are taken in Friday and the measurement happens in Monday. Similar transcellular distribution can be found due to insulin deficiency, cell destruction, or in exercise. And in exercise, obviously, it is related to hormonal reactions and acidosis. Elevated total body potassium is very rare due to increased uptake. Much more frequently can be found in decreased excretion, which is related to kidney disorders, most importantly due to decreased glomerular filtration in a kidney failure, but in some instances it is related to tubular dysfunction, for instance aldosterone deficiency, so Addison's disease, or those conditions in which the activity of aldosterone is inhibited by drugs. Hypokalemia is goes with usually as we previously discussed, hyperpolarization, and this sort of hyperpolarization will lead to decreased excitation of the muscles, and it is this decreased excitation which will lead to muscle weakness. ECG effects flattening of the T wave and prominent U waves are the most important, and it's usually accompanied by propensity to develop arrhythmias, typically torsade de pointes and the ventricular tachycardia and fibrillation. In hypokalemia, muscle weakness is related, as I mentioned, hyperpolarization and leads to flexi-depolarization. It impedes normal impulse propagation. And in the heart, arrhythmias develop due to unidirectional blocks and development of re-entry. In hyperkalemia, just the opposite is the disorder. In those instances, depolarization will lead to muscle weakness, because this sort of partial depolarization will lead to leakage and ultimately inactivation of voltage-dependent sodium channels. And therefore, the heart will stop in diastole. And the cardiac tissue becomes much prone to spontaneous depolarization. In this figure, you can see a schematic representation of the changes evoked by hypokalemia and hyperkalemia on the cardiac tissues. You can see that in hypokalemia, due to the fact that the extracellular potassium concentration is lower, the plateau phase of the action potential will dramatically change. In general, you can say that the rectifying potassium currents, the calcium currents, the relative strength of these currents will determine the length on and the slope of the plateau phase. As you can see, since the antagonizing concentration of potassium in the outer compartment is less than in normokalemia, obviously the potassium currents will be much bigger, and therefore much more negative membrane potential can be achieved with a much more pronounced potassium current. However, just the opposite is true in hyperkalemia. Since the concentration gradient in hyperkalemia is less, therefore the current potassium current is much less, and therefore the plateau phase will be shorter, and in general the membrane potential, the difference will be much less than in normal circumstances. That's why when you summarize the subendocardial and subepicardial action potentials, you will get the image that the ST will be somewhat depressed in hypokalemia, the T wave will be smaller, and the ST segment will be prolonged, and you can see a prominent U wave. Just the opposite is true for hyperkalemia. Practically the ST segment will disappear, and you will see gigantic T waves, and even the depolarization phase will be distorted, and biphasic depolarization waves will appear, and the T wave can be comparable to the ventricular depolarization wave. In the next slide, I would like to provide you a comprehensive picture of calcium and phosphate homeostasis. Nevertheless, I would like to recollect some information we discussed in the last semester regarding calcium and the phosphate regulation, specifically parrot hormone, vitamin D, calcitonin, and FGF23 metabolism. As a short introduction and summary, you can see that the major factors of
calcium and phosphate metabolism are PTH, vitamin D, and FGF hormones. PTH will facilitate calcium reabsorption in the kidney, and also it will facilitate the metabolism of vitamin D. Vitamin D will facilitate absorption of phosphate and calcium from the gastrointestinal tract, and they together will influence FGF secretion from the bone, which is the primary phosphaturic factor in the kidney, together with its receptor alpha-klotho. I would like to emphasize that not only one FGF-klotho system can be found in human being. There exists at least three important forms. One group is responsible for lipolysis and appetite regulation, while the beta it is the beta-klotho FGF21 and 19 system, while the alpha-klotho FGF23 system is primarily the regulator of phosphate concentration. Vitamin D actually is a hormone, and it is taken up as a vitamin, which is modified to to several metabolites. Through several metabolites, it is activated by the liver and by the kidney upon stimulation by parrot hormone. Parrot hormone is secreted by the parathyroid cells, as we discussed previously, by the activity of calcium sensing region. As a short summary of vitamin D metabolism, the pre-vitamin, the source of vitamin D, is activated by solar UVB radiation and this sort of photoisomerization and later activations in the kidney and in the liver and the kidney will lead to the formation of active vitamin D, which has not only skeletal effects but also important in the modulation of insulin secretion, and also important in the regulation of the immune system. It's a very, very important immune modulator. Going back to the parathyroid gland dysfunctions, as I previously mentioned, there are hyperparathyroidism. Primary is related to parathyroid adenoma. Secondary is activation of the parathyroid due to hypocalcemia. And tertiary, long-lasting, prolonged hypocalcemia will lead to the development of autonomous adenoma in the otherwise healthy parathyroid. And even after the treatment of hypocalcemia will lead to hyperparathyroidism. So primary goes with hypercalcemia, secondary goes with hypocalcemia, and tertiary will go with hypercalcemia. Hypoparathyroidism is dysfunction, decreased function of the parathyroid, or in a pseudo-hypoparathyroidism, resistance to several hormones or just the parathyroid hormone, or in some instances the condition just mimics in appearance a pseudo-hypoparathyroidism. In that case, you can see only Albright's hereditary osteodystrophy, but actually the activity of parathyroid hormone is completely unimpaired. Causes and symptoms of hyperparathyroidism. Here are the summaries, usually adenomas, hyperplasias, and carcinomas. And the symptoms are, as we discussed previously, calcification of extraocularly and nephrocalcinosis, and parallel with that, focal resorption of the bones. It is the generalized osteitis, osteitis fibrosa generalizata cystica, by von Recklinghausen. So, as a summary, lytic bone lesions parallel with extraosseal calcification. Here you can see a nice summary of the symptoms. I mentioned them in the previous semester. They are taken from your pathophysiology book. Hypoparathyroidism, as I mentioned, it can be a intrinsic dysfunction of the pareth hormone, either a congenital disorder or a secondary form, for instance, due to removal of the thyroid gland and inadvertent removal of the parathyroid glands as well, which is sometimes inevitable when you have a huge goiter, and obviously due to time limitations, there is no time for detecting the localization of thyroid glands. Pseudohypoparathyroidism, as I said, is a resistance to the parathyroid hormone. The PTH pareth hormone level is normal, parathyroid glands normal, but due to either receptor deficiency or intracellular signal transduction deficiency, the parathyroid hormone cannot exert its effects. Here you can see a short summary of the different disorders which can lead to hypoparathyroidisms due to congenital reasons, and what will be the outcome of hypoparathyroidism. Some of them we mentioned, for instance, loss of calcium due to Bartter syndrome, which means a resistance of the tubuli, or DiGeorge syndrome, which is a maldevelopment of the third and fourth pharyngeal pouches, or some other forms of hyperparathyroidisms can be elicited by immune responses, for instance, autoimmune polyendocrine syndrome type 1. And the outcome of pareth hormone deficiency are not strictly related to the morphogenesis of bone or skeletal tissues or bony tissues, because, as I said, in some instances the disorder is a much more general problem of the intracellular signaling, and symptoms of hypocalcemia hypocalcemia and skeletal symptoms. Sometimes you can see trophic abnormalities, changes in the dermatological system and in the central nervous system. Here a similar summary of hypoparathyroidism from your book, pathophysiology book, and a description of pseudo-hypoparathyroidism, Albright's osteodystrophy. Calcium concentration is regulated is a pretty strict range. Intracellularly, its concentration is very low. I would say it's negligible. You don't need to know because it is an intracellular messenger, and therefore its concentration, free calcium concentration, is limited as controlled to be as low as possible. In the plasma, it can be found in free or bound states. Complexation happens predominantly to albumin. Hypocalcemia is a condition when its concentration is lower than 2.3 millimole per liter, which, as we discussed previously, can be related to hypoparathyroidism, PTH resistance, pseudohypoparathyroidism, and very importantly due to hypomagnesemia, because magnesium is an activator of the parathyroid hormone. Also, hypocalcemia can be elicited obviously by vitamin D metabolism, which can be related to malnutrition, abnormality of the kidney and liver hydroxylation processes, and in some instances, vitamin D deficient rickets or vitamin D resistant rickets. In vitamin D deficient rickets, the patient will respond to the vitamin D, but only in excessive concentration as a dietary supplement. For instance, inactivating mutations of hydroxylase genes. When you have complete vitamin D resistance, the vitamin D receptor gene is missing. Another important thing that I would like to emphasize that calcitonin is not a really significant factor in calcium level regulation, and much more important is calcium complexation, which can develop in hungry bone syndrome, for instance, or pancreatitis. In pancreatitis, due to lipase activation, the peritoneal omental fat will be decomposed, and due to the release of fatty acids, the fatty acids will bind to potassium, calcium, magnesium, and these soaps will dramatically decrease the concentration of calcium and magnesium in the circulation. Hungry bone syndrome develops when you administer vitamin D in excessive concentration without proper supplementation of phosphate and calcium. Or it can happen in a similar manner when the subject is exposed to sunlight in early spring, and therefore the conversion to active from the sources to active vitamin D will be accelerated, and this rapid increase in vitamin D will lead to uptake of calcium and phosphate into the skeletal tissue, and accompanied by drop of calcium and phosphate in the serum. Symptoms of hypocalcemia can be summarized as increased excitation and neuromuscular irritability, paresthesias, muscle cramps, laryngospasm, tetany, and seizures are the most important things, and I would like to emphasize that these sort of ominous symptoms can cause panic in the patient, and a panicky condition will elicit hyperventilation, and hyperventilation itself will cause alkalosis, and the alkalosis will lead to dissociation of albumin, and the dissociation of albumin will lead to it's a compensatory buffering process due to increased dissociation of albumin as it gets rid of protons from the carboxyl moieties will lead to increased complexation with calcium, and therefore hyperventilation will further aggravate the symptoms of hypocalcemia and can shift the patient from latent tetany to manifested tetany. Latent tetany, the most important signs of latent tetany are the Kwastek sign and Trousseau sign. In Kwastek sign, when you tap the facial nerve on the zygomatic arch, you will elicit a smirk on the afflicted face, and in the Trousseau sign you can see a spasm, a carpal spasm of the patient upon inflation of the sphygmomanometer cuff above the systolic blood pressure for 3 minutes. On the next slide, you can see these sort of visual manifestations on in a short video. You can see the specific facial twitches, while here you can see the carpal spasm evoked by inflation of the sphygmomanometer cuff on the upper arm in pronated position, the typical deer's head position develops. Hypercalcemia is a condition when the calcium level is bigger than 2.7 millimole per liter. It can be related, as we discussed previously, primary or tertiary hyperparathyroidism. In the primary one, multiple endocrine neoplasias, or mono or biallelic inactivation of the calcium sensing receptor genes are responsible for the disorder. In a pseudo hyperparathyroidism, other hormones which mimic the activity of the parad hormone are responsible for hypercalcemia. They are usually cytokines. Also, some other conditions can lead to hypercalcemia, which evokes increased remodeling of the bone or increased catabolism of the skeletal tissue, like in acromegaly or Cushing's disease. Also, hypercalcemia develops in vitamin D toxicity, or since vitamin A is a cofactor of vitamin D, overdose of vitamin A will elicit the same issue. Similarly, increased bone reabsorption due to metastasis, immobilization, due to increased intestinal absorption, and mainly due to decreased renal excretion, which can be related to congenital disorders or other conditions, acquired conditions, and last but not least, abnormal skeletal development, typically a dynamic bone disease due to immobilization or some forms of intoxication. When in hemodialysis, the equipment is not properly maintained. and aluminium intoxication can develop either from the equipment or the dialysis fluid. Hypercalcemia symptoms can be summarized according to as bones, stones, groans, and moans. Moans is a summary for the hyperpolarization evoked nervous system symptoms, which is characterized by drowsiness, lassitude, depression, and ultimately stupor and coma. The gastrointestinal symptoms are a bit more complicated and sometimes related to the urogenital symptoms. Some of them are related to increased calcium complexation and stone formation. It is related to metastatic calcification. But also it's important to emphasize that the majority of the gastrointestinal hormones require calcium-dependent signal transduction, and therefore these hormones, oversecretion of these hormones, will lead to hypermotility and oversecretion of gastric acid. Also, we should mention nephrolithiasis and nephrocalcinosis, which is an important thing, and the cardiac symptoms are in sharp contrast with hypocalcemia, while in hypocalcemia, prolongation of the QT interval can be detected due to the fact that calcium flux is less and therefore cannot oppose as efficiently as in normal circumstances the rectifying potassium currents. In hypercalcemia, you can see just the opposite. Immense flux of calcium will elicit shortening of the QT interval. In some instances, when the cause of hypercalcemia is hyperparathyroidism, obviously you can see osteitis fibrosa generalizata cystica. In this figure, you can see a short summary of hypo and hypercalcemia, all the important symptoms which you should memorize for the final exam can be found here. The regulatory factors, the factors which influence the dissociation of calcium from the carrier molecules, from the complexation, and the symptoms of the cardiac tissue and the other organs. Phosphate. Phosphate is regulated in a parallel manner with calcium. As I mentioned, FGF, regarding the FGF23, vitamin D, and parent hormone system. It's of crucial importance, especially in the intracellular compartment, because it takes part in cell signaling as a component of CAMP and cyclic GMP. Also, the source of kinases. It as an important cofactor in a macroergic phosphate, in the form of macroergic phosphate. It's an energy resource, and obviously it's a structural component of phospholipids, nucleic acids, and skeletal tissue. Its main source is the plants. Hypophosphatemia is a condition when phosphate concentration drops, inorganic phosphate concentration drops below 0.81 millimole per liter, and the main cause of it is transcellular distribution, which can be related to alkalosis when phosphate enters the cell, or due to recovery when the recuperating patient consumes more food, and lots of ATP and creatine phosphate is produced intracellularly, which will obviously tap the extracellular compartment and can lead to lethal hypophosphatemia. Similar activity of some hormones can be demonstrated, which will lead to the formation of phosphorylated compounds and macroergic phosphates, and therefore can lead to critical drop in the phosphate concentration. Skeletal deposition and formation of bony tissues can lead to hypocalcemia as well as hypophosphatemia, like in hungry bone syndrome or osteopetrosis. Decreased phosphate absorption can be demonstrated in fasting or vitamin D deficiency, so in malnutrition, or increased complexation like antacid abuse or some forms of diarrhea. Increased urinary excretion typically is related to congenital can be related to congenital disorders in which phosphate transporters are missing in the patient, for instance in a Fanconi syndrome, or FGF23 overproduction, or primary hyperparathyroidism, or as in secondary instances, secondary hyperparathyroidism. Hypophosphatemia will go with decreased, if it is not the cause, it will lead to decreased ATP and creatine phosphate production and decreased concentration of macroergic compounds, which will lead to disruption of cellular functions, so hemolytic anemia, decreased oxygen carrying capacity due to 2,3-diphosphoglycerol concentration, platelet leukocyte dysfunction, muscle weakness, decreased mental acuity, paresthesia, decreased nerve conduction, decreased contractility of the cardiovascular tissue, GFR drops, and abnormality of the tubular transport processes. Hyperphosphatemia again can be elicited by abnormality of the transcellular distribution. Usually, since the intracellular concentration of phosphate is huge compared to the extracellular, and as you can see, over 1.5 millimole per liter, you can detect hyperphosphatemia. A pretty minimal increase in phosphate concentration can lead to severe problems, and a minor disruption of the transcellular transport can lead to such a condition. For therefore, tumor lysis syndromes, leukemias, rhabdomyolysis evoked by, for instance, status epilepticus, bowel infarction, malignant hyperthermia, it can lead to such hyperphosphatemia. In some instances, indeed, increased exogenous load can lead to it, for instance, vitamin D intoxication or cow's milk feeding to premature babies. That's why cow's milk administration is not or feeding is not recommended to babies before 1 year. One reason for that. Reduced urinary phosphate excretion is one of the most important things, because phosphate, as I said, is a waste product which is taken up from plants, because in plants, phosphate is the most important extracellular anion as well. So it's the kidney's role, the surplus amount of phosphate. If it cannot serve that function, for instance, in renal failure, obviously hyperphosphatemia will develop. Also, you can see such situation developing such situation in pseudohypoparathyroidism, or in the case of increased phosphate reabsorption when FGF23 is missing or the Clot2 receptor is missing. Increased bone reabsorption, like in osteoporosis, or can lead to a similar disorder, but it can be also found in the form of pseudohyperphosphatemia, which is absolutely the same condition as pseudohyperkalemia. It's a laboratory artifact due to prolonged storage of laboratory samples, and due to hypoxia and due to decreased energy supply from the red blood cells, mainly from the red blood cells, phosphate will leak out into the serum. Consequences of hyperphosphatemia can be easily summarized as hypocalcemia, because phosphate will bind immediately calcium. It will form calcium complexes, and this sort of complexation will lead to rapid drop in calcium level. And also, it will lead to decreased formation of vitamin D, and on a long term, this sort of complexation will lead to extraosseal calcification, and extraosseal calcification and increased complexation will lead to oversecretion of parathyroid hormone. Oversecretion of parathyroid hormone will lead to osteitis. Here you can see a summary of phosphate abnormalities. Here, the most important is the calcium complexation process. So when you increase phosphate, since the constant dissociation constants should remain the same, obviously increase in phosphate will lead to decrease in calcium, and as a result of them will lead this sort of complexation will lead to increased formation of calcium phosphate. So parallel with moderate increase in phosphate and moderate decrease in calcium, in the numerator you can see a moderate increase in the denominator. In hyperphosphatemia, therefore, parallel with hypocalcemia, you can see a calcium phosphate precipitation in the viscera and the soft tissues. In hypophosphatemia, as I said, the ATP supply deficiency is the most important outcome. And the reasons are related to either transcellular distribution problems or hormonal problems. Here I would like to show you a comparison, a synopsis of the most important skeletal tissue disorders, and to emphasize the most striking differences in features. The first one is osteomalacia, which is related to vitamin D deficiency. It can appear in the young and in the adult. And in the adult, it is the true osteomalacia, which goes with bone tenderness and sometimes fractures. Much more severe is the disorder which develops in the young, which is called rickets. Rickets will lead to severe malformation of the skeletal tissue, both legs, knock knees, pigeon chest, kyphoscoliosis, and it is always related to the selective loss of inorganic components of bony tissues. Typically, it develops in vitamin D deficiency, vitamin D dependent, and vitamin D resistant rickets. Osteoporosis is a completely different kettle of fish. Here you can see a general loss of both the organic and inorganic components of bony tissues. It is most frequent in postmenopausal women, but characteristic of immobilization as well. In postmenopausal osteoporosis, the most important factor is estrogen deficiency. I would like to emphasize the normal function of estrogen in the normal skeletal homeostasis. Estrogen is important in the differentiation of osteoblasts, and also it will inhibit the osteolytic activity of osteoclasts. It's very important. So it maintains the normal metabolism and decreases the resorption process. If estrogen is missing, bone reabsorption will increase, and parallel with it, due to dysfunction of the osteoblasts, mechanosensing will decrease as well. In the next chapter, I would like to cover magnesium balance and the functions, physiologic functions and pathophysiology of magnesium deficiency and toxicity. Magnesium is a very common cation, both in the extra and intracellular compartment. It is an enzyme activator and antagonizes calcium activity. One of the most important actions is outlined here. As you can see, B6 and magnesium play a role in the formation of GABA through the action of glutamate decarboxylase. In order to understand the importance of this enzyme and the deficiency of the co-activators, you are supposed to recall that glutamate is the most important activatory neurotransmitter in the central nervous system, while GABA is the most important inhibitor in the brain. So when the enzyme cannot function properly due to coenzyme deficiencies, glutamate GABA ratio will favor excitation, while normal supply of B6 and magnesium will favor GABA activity. Here, as usual, I would say you can see the magnesium metabolism in a synoptic figure, hypermagnesemia and hypomagnesemia, and the consequences are covered here. hypermagnesemia is a relatively rare condition, and usually it is related to kidney failure because magnesium is a plant derivative, because in chlorophyll instead iron you can find magnesium, not, unlike in heme, and magnesium therefore must be excreted as a waste product of plant origin. Also, it can be influenced by cellular transport, for instance in diabetes, when the uptake into the cells is less than normal circumstances, since relatively magnesium concentration is higher than in the extracellular compartment. The outcome will be prominent action will be inhibition of calcium action, and it can lead to decreased neuromuscular activity, hyperreflexia, decreased mentation, somnolence, or even coma. The opposite is true for hypomagnesemia, which is much more common. Parallel with decreased uptake, you can see it in selective or general losses through the kidney, for instance, upon activity of diuretics, or in salt-losing nephritis, or osmotic diuresis. Also, it's important that magnesium can be lost due to complexation in pancreatitis, and can be the deficiency can be elicited by malabsorption syndromes. As in general, hypomagnesemia is related to symptoms of hypomagnesemia are related to two factors. One thing, that it cannot antagonize the activity of calcium. Second, concentration of GABA will drop precipitously compared to glutamate, and some indirect action is also of great importance, because magnesium is a co-activator of PTH, so magnesium will influence calcium level as well. So due to hypocalcemia, due to decreased antagonizing activity, and due to decreased GABA level, in a general increased neuromuscular excitability, hyperreflexia, cramps, and also in the circulation, propensity for arrhythmias and tachycardia are common. This sort of summarization here expounded in a much more detailed manner. Let's start with hypomagnesemia, which can be detected when magnesium level is below 0.7 millimole per liter, decreased absorption, decreased uptake, increased complexation, or renal losses, as I mentioned, some congenital kidney disorders, some forms of increased fluid transport like diuretics, or acquired cases of hypo or astenuria, when the kidney tubuli cannot operate functionally, can lead to hypomagnesemia. In chronic alcoholism, several factors can lead to the complex disorder, decreased uptake, and together with increased gastrointestinal and kidney loss. As I said, the clinical manifestation of hypomagnesemia can be grouped into three parts, causative parts: decreased GABA concentration, decreased antagonization of calcium action, and also an important thing that decreased calcium concentration due to the fact that calcium is regulated by Perret hormone, and Perret hormone is activated by magnesium. So while the intracellular signal transduction with calcium is unimpaired, the hypocalcemia evoked depolarization, which leads to hyperactivity, is more aggravated by hypomagnesemia. Regarding the signal transduction, most important symptoms are related to enzymatic dysfunctions, because magnesium is a important component, important co-activator of several enzymes which take part in carbohydrate metabolism. Cardiovascularly, the most important symptom is increased propensity to cardiovascular arrhythmias, and since magnesium is an important component of the skeletal system, osteoporosis or osteomalacia can develop in the patient. Hypermagnesemia, which can be detected when the extracellular concentration is bigger than 1.1 millimole per liter, is a relatively much rarer condition. The most important reason is renal insufficiency, when you cannot get rid of the herbal waste products, which are potassium, phosphate, and magnesium. Typically, in some instances, magnesium supply exceeds renal excretion, which can be of endogenous source or exogenous. Actually, the endogenous forms are related to a transmembrane shift, reversible or irreversible, since magnesium concentration is much bigger intracellular than extracellular. Exogenous is pretty rare. Only it is usually related to malpractice due to treatment with a high concentration of magnesium containing laxatives, which are cathartics and very strong laxatives or some antacids. Increased renal magnesium absorption is pretty rare when the magnesium transport is since magnesium competes on a calcium transporter, and when calcium transport is facilitated together with calcium, magnesium can be taken up as well. Clinical manifestations of hypermagnesemia are related to inhibition of cardiovascular and neuromuscular functions of calcium, so hypotension, bradycardia are the typical signs, and neuromuscularly muscle weakness, even paralysis of voluntary muscles, respiratory depression and hypoventilation, while in the CNS lassitude, malaise, decreased mentation, vertigo, nauseation, vomiting, and ultimately coma. The next chapter is just a short overview of how closely correlated is cobalt and sulfur metabolism, and I would like to emphasize two important activities of B12, which is a cobalt containing vitamin. Why is it so important? Because, as you can see, B12 works as the ultimate regulator of folate metabolism, and as a master regulator of the folate trap here in the form of methylcobalamin, while here as adenosylcobalamin will influence phospholipid metabolism. So, due to methylcobalamin deficiency, the methionine cycle will be impaired, and the outcome will be folate deficiency. And due to folate deficiency, there will be a discrepancy of RNA and DNA metabolism, while RNA production is unimpaired due to the synthesis of uric acid. Due to folate deficiency, DNA synthesis is inefficient, and therefore formation of deoxythymidinic acid will be impaired. And deoxythymidinic acid is an important component of DNA synthesis. Megaloblastic anemia will develop, in which the cell can grow. The plasma of the cell can grow due to unimpaired RNA synthesis, while the cell cannot divide due to decreased replication rate. Another important thing is adenosylcobalamin deficiency, when due to phospholipid synthesis abnormality, the myosin sheet production will be sluggish, and those axons, neurites, which have the thickest myosin sheet will over time will degenerate, and this sort of degeneration will lead to so-called funicular myelosis, which is a very important component of B12 deficiency, pernicious anemia. In pernicious anemia, due to an autoimmune disorder, B12 uptake is completely missing because the intrinsic factor is attacked by the immune system. So megaloblastosis parallel with central nervous system degeneration will produce the most important symptoms, and these neuronal symptoms, neurologic symptoms cannot be detected in isolated folic acid deficiency. That's the main difference between the two forms of megaloblastic anemias. In the following figures and slides, we will discuss the pathophysiology of trace elements, which are absolutely essential, but only in a limited amount for your body. First, we should start with zinc. Zinc is a component of hundreds of enzymes, and most importantly, takes part in the regulation of transcription, and in the form of zinc fingers. Therefore, zinc deficiency is a quite important disorder which can be related to malabsorption or complexation due to iatrogenic reasons or other forms of complexation like in steatorrhea, or congenital abnormality of zinc transport, for instance, in acrodermatitis enteropathica. Increased demand is another common issue, typically in newborns or in pregnancy, and some instances in kidney failure, typically in compensatory polyuria states, you can see increased loss. Symptoms of zinc deficiency obviously will demonstrate itself mainly on in those target organs which show very high transcription rate. So you can find skin symptoms, mucous membrane symptoms, retardation of growth, anemia, hypo and hypogonadism. In some severe instances, you can find even decreased mentation lassitude. From the other trace elements, manganese is one of the most important because it is not only a component of the skeletal tissues but also coenzyme of several enzymes like superoxide dismutases, arginase, and glutamine synthetase. When the concentration decreases parallel with impaired bone growth, mental retardation, and the infertility can develop. But the most potent is the toxicity, which leads to decreased glutamic acid concentration and Parkinson's disease. Cobalt, as I mentioned previously and described, is most commonly is missing in pernicious anemia, which leads to megaloblastosis and macrocytic anemia, and also funicular myelosis, peripheral and later central nervous system neurodegeneration, which will go with ultimately dementia and paralysis. Toxicity is much rarer. It will lead to carcinogenesis and cardiomyopathy. Chromium, it is a cofactor of insulin, therefore it will lead, deficiency will lead to impaired glucose tolerance, while toxicity is much more common, like nickel. It causes contact dermatitis, and the hexavalent ion is extremely hazardous because it's carcinogenic. Molybdenum is component of the enamel and several enzymes as a cofactor. Usually, the most important symptoms are related to deficiency because it will afflict sulfur and purine metabolism. While toxicity is related to the competition between molybdenum and copper, and which leads to the symptoms of copper deficiency. Iodine, it's quite easy to recollect. Iodine deficiency will lead to either cretinism or myxedema, while toxicity will impair oxidation and transport of iodine, because iodine in a surplus concentration will impair the transcription and translation of the transporters and oxidative enzymes of thyroid hormone synthesis. Rarely, in a diseased, sick, inflamed thyroid gland, uptake of iodine cannot be further regulated, and paradoxically, in very inflamed thyroid gland, in sharp contrast with the normal inhibitory action of toxic level of iodine, which is known as Wolff-Chaikoff phenomenon or Wolff-Chaikov's effect. Paradoxically, in those patients, Jod-Basedow phenomenon will develop, so further increase in iodine will elicit not inhibition but activation. That's why in the form of tempering of the thyroid gland pre-operatively, you must be very careful. Selenium is extremely important antioxidant substance in severe gastrointestinal diseases or in disorders when the soil selenium concentration is low. Oxidative processes will be aggravated. And since selenium is a component of as coenzyme of those factors which influence thyroid hormone metabolism, selenium deficiency definitely will aggravate the symptoms of iodine deficiency. Altogether, you can see trophic abnormalities of the skin and appendages, and also over time myocardium necrosis, cardiomyopathy can develop. It is called Cashhound's disease. Fluoride is a well-known factor, typically the deficiency, since you know that it's an important component as of the animal as fluoride appetite, but also important to emphasize that equally important is the toxicity, which was pretty recently clarified. The symptoms and the sources of toxicity. You should know that the feed stocks of Teflon procession, typically polytetrafluoroethylene, contamination can lead to fluorosis. It's not only an aesthetic or cosmetic problem, maybe it will lead to mottled animal, but also it will influence the normal growth of the bones, since it will lead to early sclerosis of the epiphyseal plates, exostosis, and abnormal growth of the extremities. Also, extraocular calcification will be accompanied by carcinogenesis, and in afflicted population, the rate of cancer is several times higher than in the normal population. Copper metabolism is very important disorder because the background, first the ion is extremely important in our metabolic processes, namely in oxidative phosphorylation, since it's a component of cytochrome C oxidase. Second, because its background is pretty well clarified. Copper, there are two important disorders which are related to copper metabolism. The first one is toxicity, and you can find an increased avidity to copper And this increased avidity will lead to accumulation of copper in different tissues, namely in the central nervous system and the eyes and in the liver. While the opposite is deficiency, which can be related to decreased absorption or decreased transport of copper due to missing transporter of ceruloplasmin. In deficiency, the most important thing is impaired proliferation of the nervous tissue, mainly the central nervous system, proliferation and differentiation, and also you can detect other ectodermal tissue problems, typically the skin and the skin appendages. Here you can see a short summarization of the symptoms of Wilson's disease, copper toxicity, and the causative genetical problems, transport problems of copper metabolism. As you can see, that transporter which afflicts the excretion of copper into the bile will be mutated in Wilson's disease. While in Menkes disease, the most important problem is decreased absorption of copper. In Wilson's disease, due to the central nervous system accumulation, you can see degeneration in the basal ganglia, typically in the lenticular nuclei, subthalamic nuclei, and it will lead to hyperkinesia. It's called atetosis, and or bellism. Accumulation of copper in the cornea will lead to the Kaiser-Fleischer ring formation, and in the liver, without treatment, micronodular cirrhosis will develop. Iron. Iron deficiency is of crucial importance in human beings because in modern life, as we evolved into food producing society, or formerly food producing society, we started to consume huge amount of cereals and much less meat and vegetables. So the iron supply became limited. In the past 10,000 years, unfortunately, it evoked or facilitated the development of mutations in the human population. It led to increased avidity of human beings toward iron. Absorption is much higher than previously because our supply was much more limited, typically in the during the industrial revolution. And iron is absolutely important in every human cell. Obviously, in those cells which contain mitochondria, the oxidative phosphorylation speaks for itself because cytochromes contain iron. But also in the red blood cell, it plays an important role, despite the fact that it doesn't contain mitochondria. Heme is an important component. So all the cells which show high division rate will suffer a lot from iron deficiency. Another important aspect is, however, that in modern era, due to several campaigns, iron uptake, iron supply became a very important aspect of our life, and unfortunately, especially in males, iron toxicity can develop with a specific genetical background. Why? Because those subjects or those populations who previously was afflicted most by iron deficiency, as I said, has much higher iron avidity and much higher level of iron absorption. In females, it doesn't cause any problem because previously iron deficiency anemia and the symptoms developed in females. So in those subjects, it was a must to have such genes which can compensate for loss of blood during the menstruation cycle. Now the opposite is true. The iron supply is optimal, and therefore males will suffer from iron toxicity if they carry those genes which are responsible for increased iron uptake. Iron uptake and storage regulated or happens through two pathways. The first one, which should be emphasized and mentioned, that the most efficient way of iron uptake is heme. It's about 10 times more efficient than the uptake in the form of iron. Ferrous iron is the only form of iron which can be transported through the membrane, so ferric iron must be first reduced to ferrous iron in an acidic environment with the help of vitamin C. This sort of process will yield ferrous iron which can be taken up, stored, or can be transported to the basolateral membrane with the help of ferroportin. And the bound iron in the form of transferrin will be taken up by the liver cells. It's very important that the whole process in several points is regulated by HFE molecule, which is a abbreviation for high Fe, high ferrous, and it is the most important culprit gene which will elicit hereditary hemochromatosis in the adult form. Other mutations which will favor increased iron uptake are much more severe genetical disorders, and these genetic disorders will elicit juvenile forms of hemochromatosis. Iron deficiency. As I said, iron deficiency can be related to decreased uptake, which is very common in vegetarians because they don't consume enough heme. Decreased absorption can be related to decreased gastric juice formation or due to malabsorption disorders or complexation of ferrous iron with other chelate-forming molecules. Also, disorders of utilization, for instance, in sideroblastic anemias or porphyrias, can be responsible for the symptoms of iron deficiency. And the increased loss, as I mentioned, in women, it's very, very common symptom. cause. Symptoms will afflict hemoglobin, myoglobin, synthesis, proliferation of the epithelial cells, and ultimately the previous symptoms will lead to anemia, hypochromic anemia, hypoxia, while decreased myoglobin synthesis will lead to weakness and fatigue. Altogether, due to hypoxia, will lead to increased cardiac output, tachycardia, systolic murmur, and ultimately heart failure. Due to dysplasia of the ectodermal tissues, pharyngitis, esophagitis, atrophic glossitis, and even pharyngeal carcinoma can develop. In the skin, you can see angular stomatitis or chelosis, koilonychia, spoon-shaped nail, and brittle hair. Here a short visual summary for the symptoms, which are very common and you can observe in several patients. Spoon-shaped nail. Here, Plummer-Vinson syndrome evoked glossitis and angular stomatitis. Iron toxicity, as I mentioned, is related to either HFE mutation or much early due to juvenile forms in which ferroportin, hemojuvelin, ceruloplasmin, transferrin or transferrin receptor are mutated. Nevertheless, it is the most frequent monogenic inborn error in the Caucasian population, more frequent than cystic fibrosis or even selective IgA deficiency. In iron toxicity, you must differentiate, you have to clearly differentiate hemochromatosis with secondary iron deposition called hemosiderosis. Hemosiderosis is a relatively benign disorder which is related to chronic inflammatory disorders, chronic hemolysis like thalassemia or sickle cell anemia, and you can detect the increased deposition of ferritin in several tissues, but it will not interfere. Deposition in the form of ferritin, it will not interfere with the normal life of the cells. It doesn't reach the toxic level. However, in hemochromatosis, it's a long-lasting process, excessive accumulation of iron, and it will lead to cardiomyopathy, cerebral and ocular symptoms, definitely liver cirrhosis and hepatocellular carcinoma, which is the most feared complication of hemochromatosis. Endocrinopathy, typically pancreatitis, testicular atrophy due to usually pituitary disorder, arthritis, and skin pigmentation. Due to skin pigmentation and the diabetes, you will call the syndrome bronze diabetes. Here you can see secondary iron deposition disorder, hemosiderosis, and in sharp contrast, the much more aggravating symptomatic constellation of hemochromatosis. Here you can see that liver cirrhosis, even liver carcinoma, can develop skin pigmentation, cardiomyopathy, diabetes with chronic pancreatitis, pituitary dysfunction, and hypogonadism are the most important symptoms.